Good morning, everybody. Today we will continue to talk about Gauss's law and use Gauss's law to solve some problems. We may have time to just touch on the electric potential, but we will spend most of our next class on the electric potential. Okay, so we talked about Gauss's law. Here is just a really quick check-in to see if we remember what Gauss's law is. Here is a question. I'm gonna go ahead and launch the poll for you. There's no need to go to the breakout rooms, so maybe take a minute or a minute and a half for this question. Okay, 10 more seconds. Okay, I'm gonna go ahead and end poll, and then I'll share the results. Here's our results. It's asking what can we say about the total electric flux through the surface, E dot into dl, and whether that is Q over epsilon naught, or maybe we need more information to share, or maybe it's not. Okay, so majority of us voted for A. So what does Gauss's law say? Gauss's law saying that E dot into dl, actually the double integral or triple integral, or if it's just single, you can use one single to represent all three. You can look at what is integrated over is dA or d tau or dl to know if it's the surface or line or volume. So but I usually try in my writing, try to always say the double if I just write the double, just try to be consistent, but you know that you can just use one integration sign to represent all of them. Okay, Gauss's law, E dot into dA is Q enclosed over epsilon naught. That is Gauss's law. Okay, this is Gauss's law. And Q enclosed is enclosed by this area, the closed surface. So in this case, it is telling a Gaussian surface, which is not a sphere, has a single charge in it. By looking at this, realize that it doesn't really specify what your what the shape of your surface has to be. It can be any kind of shape, as long as you enclose that amount of charge. You're gonna get Q over epsilon naught. So A is correct answer. Now, one way to think about this, how come that the area doesn't matter, is if I may use an analogy, let's say you build sort of a surface around a water faucet, right? And the Q enclosed in this case can be thinking about how many faucets you're enclosing. Maybe you're enclosing one, right, or two. And you can't really see the faucets. You can't really see the source. All you can see is the amount of water flowing out of sort of this barrier that you built. You can see that it doesn't really matter the shape of the barrier you have. The water flow is simply the water flow, and Q enclosed will be the same. Of course, that to actually calculate this flux, if you choose your surface, for example, for the point charge, obviously we wanted to simplify our calculation. Now we will always choose a spherical surface because that calculation is easier. in that the E is in the r hat direction and our dA is also in the r hat direction. So this calculation is actually doable. But that doesn't mean that you cannot choose a random surface for this relationship to still be true. You can choose a different surface, a random surface. Then you might argue then overall the surface area changed. Well, that is true. However, the E field also at different location also is not the same as before when you had a spherical surface. But overall, if you could somehow calculate the flux using numerical calculation, you will be able to get the exact same answer as before. So the correct answer is A. So Gauss's law is always true. We say Gauss's law is always true, meaning that this relationship always holds. But Gauss's law is not always useful, meaning that we cannot always use Gauss's law to solve for E field. Now, if we want to solve for E, we should be able to take E outside of the integral. So there are two conditions that needs to be met in order for Gauss's law to be useful. So what do you think those two conditions are?
The surface that you have has to be a closed surface, and the surface that you create has to have a charge enclosed.
Right, so that would be, in order for you to construct a Gauss's law, you need a closed surface, and there has to be, well, now you can enclose zero charge. In that case, you would just have a zero flux, which is also fine. So for example, if I enclose a surface here, you can see it's outside of my charge, right? I'm enclosing zero charge. So Q enclosed here is zero. And my flux, you can see E field is coming in and going out. The same that comes in also leaves. So I have zero flux. So you can enclose zero charge. It's just not going to be, I'm sorry. Sometimes you can also even use that to find E. So it is also can be useful. So there are two conditions that needs to be met in order for Gauss's law to be useful. So when I mean useful, let's take a look at what our Gauss's law looks like. Right now, E is inside this integration. For it to be useful, I need to take E out. I need to be able to make this into something like E times some kind of area gives me Q enclosed over epsilon naught, because you're solving for E. Useful means that you are solving for E. So only when you can take E out of the integral, you can solve for E is equal to blah, 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 right? So now we put our focus here. So in what condition are we able to take E outside of the integration?
When it's uniform?
Yes, so E has to be, so whatever your surface is, E has to be a constant on the surface. Okay, there is one more condition. You can see this is a dot product, so it has to do with vectors.
Right, so they both have to be vectors. Your dA has to be a vector, so you have to construct it.
Right, so
has to be symmetric.
Yes, so you mean with symmetric, I think you meant you want your area to be, you choose your area to be a certain way so that the dot product is easy to calculate. For example, if you have a point charge or spherical symmetry, you use the sphere as your spherical surface, your Gaussian surface, because that dA is in the same direction as E. Well, if dA is, sometimes dA is have multiple sides, right? Like you have a cylinder, then you have the barrel, you have the top and bottom, so you have multiple sides. So either you want E to be parallel to dA, or you want E and or to be perpendicular to dA, because both of those situations, the dot product is actually easy to calculate. Is easy to compute. So you need those two conditions to be met for Gauss's law to be useful. So now let's actually use Gauss's law to solve the problem we did in the previous class. That was quite complicated. We use integration to do this, but now let's do Gauss's law. Okay, so we have a uniform charge density. So throughout this volume, right, this is a volume integration, a volume charge with rho, that's uniform. We want to find E field outside of this unit solid sphere. And I argue Gauss's law is useful here. So I argue Gauss's law is useful, meaning that I'm able to find a surface. I can find a surface so that those two conditions are met, so that E is parallel to dA or perpendicular on some sides, and E is constant on the particular surface. Not saying E is constant everywhere, but just on the surface that you choose. So I argue that I can find such a surface. So you realize in order to be able to find a surface, you first need to figure out the direction of E and the dependence of E. Otherwise, you cannot argue whether E is parallel. You want a surface to pay parallel to E, but what is E, right? In what direction? So the first step to do this problem is to analyze the symmetry and figure out the direction and dependence of E. You have done this, once you have done this multiple times, it becomes so internalized and you don't do them explicitly. But I think it's a good practice to at some point make this very explicit. Once you're familiar, you don't always have to do this exercise. So first, let's think about the direction of E. We're giving a sphere. So I want to use the spherical coordinates, which means E can either be r hat, theta hat, or phi hat direction in the spherical coordinates. So what direction do you think E will be in this case?
R hat?
R hat. Yes, that is correct. And why is that? How do you know?
Because the field lines are always pointing away from the charge. And you can consider all the charge at a point in the center.
Very good point. Once we did the calculation, we realized a solid sphere is equivalent to having all the charge concentrated in the center in terms of the E field. That's something you already know, but right now we don't know that fact yet, right? We just want to figure out, okay, what is the direction of E? In the previous lecture, we have done this. Remember, we say, okay, we choose a random point P outside. P can be anywhere, right? We decide to put Z-axis along with this random P point so that our E field is always on the Z direction, in the Z direction. And you realize that no matter which point you choose, you can always sort of thinking about poking a needle through the center of this sphere, and it doesn't make any difference. You can call that Z previously, and now you can call that R direction, right? Whether it is here, or if your P is here, or if your P is here, or if your P is here, no matter where you are, you realize, oh, it is actually a R hat direction. So that is our direction of E, which means we want to choose a surface so that the dA is also in the R hat direction. So that indicates you want a spherical Gaussian surface. The second thing we want to analyze is the dependence of E. Dependence means that as these variable changes, E changes value. So as R changes, meaning that when you go further or closer to the center, your E changes value. Theta is the angle with respect to Z, and phi is the angle with respect to X direction. So do you think E depends on some of these variables? Which variable or
It would
variable?
only depend on R.
It would only depend on R. Very good, Mitchell. And why do you think that is?
Because the thing that matters is the distance from the sphere, which is represented by R, because it's symmetrical everywhere else.
It has the spherical symmetry. Very
Yeah.
good. This is very important and help us simplify the situation. If you look at a sphere, if you rotate, your head around the Z, you're still looking at the same sphere or globe. If you rotate phi direction, you're still looking at the exact same thing. There is nothing that changed that made you realize you're looking at something different. Like if someone holds a uniform ball in front of you and simply just rotate one way or another, you're not going to notice a difference. So because of the spherical symmetry, it should not depend on theta or phi, okay? Because you're not looking at a different physical setup. So E can only depend on R, meaning that as you get closer to the center or as you get further away to your source, then E should change, and that's physical. That makes sense. So now we have decided that we want to choose a Gaussian surface. So let's draw the surface together. We're going to draw our Gaussian surface. So randomly somewhere outside of the surface, I'm going to put it here. Use a different color. Put it here. I'm going to draw a sphere. This is my Gaussian surface. Okay, so this is called Gaussian surface. It's a sphere. And I have met the condition that dA is in R hat direction. And do I meet the other condition that is E uniform on this surface? That,
Well, it carries uniform charge density, so the E field should be the same.
yes, E only depend on R. Yeah, so you can see whether you're looking at this point or this point or this point, anywhere on the surface, you are at the same distance away from your center, from the source. So E is uniform. E is uniform or on dA. Okay, so I've met those two conditions. You can see the process is a little bit lengthy, but once you went through it, you know the reason behind and why you can solve the problem this way. Okay, so the rest will be easy. So let's go ahead and solve it. We do E dot into dA is equal to Q enclosed over epsilon naught, right? Because you are using Gauss's law. And in this case, my E is parallel to dA, so I'm going to rewrite that using E magnitude times dA magnitude. I can get rid of the vector signs, dot product. So that's the first step. And the second step is U is constant on the surface, so you can take E outside of your integration. And someone asked earlier, what does this become? Does that become 4 pi r squared? Yes, you're right. This is the surface of your Gaussian surface. So my Gaussian surface is at a distance r away from the center. So my overall area of the sphere becomes what? 4 pi little r squared, right? R here you can see is a variable. Q enclosed, total charge enclosed by this yellow surface I draw. So it's the total charge enclosed. And so here the problem usually give it one or two ways. one way that the problem usually give you is the total charge. It either simply just tell you that Q is given and give you a radius R. Now in this case, it's
have
giving
charge
you
density.
density rho and radius R. Either way is fine. And let's stick with the rho situation. Okay, so give you rho and a radius R. Let's we should know that. Okay, so this is given. Okay, so total Q enclosed. What is Q enclosed?
Rho v.
Rho times volume, and the volume of the sphere is?
4/3 pi r cubed.
Okay, very good. So we have our Q enclosed. You can calculate your E to be rho R third epsilon naught R squared, like this, 3. Okay. And once you're done, don't forget to add the direction. This is a magnitude, but we already using our symmetry analysis. E is in the R hat direction. So add your direction for outside. Okay. Now, what if I ask you, what is the E field inside? So going back to this picture, and I'm asking you, what if you are looking at E field inside at this random point, which is still at a location R away from center? So how do we calculate it if it's asking inside? What would the first step be? Same thing. Okay, so we still have the same symmetry. So again, we need Gaussian surface. So let's draw the Gaussian surface. If it's inside, my Gaussian surface should be inside. Because you're always calculating your E on the surface. So if you're curious about this point, you need to put your surface exactly running through that point. So draw a new Gaussian surface running through the point P, and use the same formula. Maybe your Q is different now. Okay, so outside, for outside, now let's calculate inside. Everything is the same, so you can see that my left-hand side is still E 4 pi R squared. R is a variable. Right now, R is less than, this is when R is larger than R. Right now, R is less than R. Okay, so what is my Q enclosed? It's a different value now. So what is?
Right. It's would we be calculating the volume of the Gaussian surface we created inside the sphere?
Yes, it's whatever is enclosed by your surface.
Is it a ratio of the charge densities between the big sphere and the Gaussian surface?
It is a ratio, yes. It's proportional. It's a portion of the total charge. So you used to have the entire radius capital R, but now you only have a portion of that, which is little r. Yes, very good. So again, charge enclosed is exactly the same as before. Density times volume. So the volume now is 4/3 pi what cubed?
Little r cubed.
Little r cubed. You're enclosing only a little r. The other part is outside of your Gaussian surface. You are not enclosing it. So that would be our answer. Again, you can get E to be rho over 3 epsilon naught R. It's linearly increasing with R. Okay, E has directions, put the a hat on for inside. Okay, so outside, inside. Does it make sense that my E, now if I were to draw how this behaves as a function, whoops, I don't know why that went away, okay. Or had R 3 epsilon naught. So if I were to draw a function of E with respect to R at R, So inside, right? Outside. It looks like this. Inside is increasing as function of r. Outside is decreasing with the power law 1 of r squared. Does that make sense?
It does.
And why does it increase inside as a function of r?
Because as you expand your Gaussian surface, you're enclosing more and more charge.
I am enclosing more and more charge, but can I argue I'm also getting further away by increasing r?
Yes, but the math should work out because you have r as a constant. R will be multiplied against your other constants to increase E. It isn't until it becomes an inverse square law where things begin to drop off.
Yeah, the inside, the increase of my volume is faster than my decrease of the increase of the distance. My distance is 4 pi r squared. My volume is r cubed. So my r cubed is actually faster, given that I'm still overall increasing my E field as I increase more, enclosing more volume. Very good. So I enclose more charge, my E increase. And overall, you can see once you reached at R, you cannot enclose any more charges. You can put as big of a Gaussian surface as you want, but you can see you're still enclosing just the sphere, but nothing more than that. Right, so that's why when you're doing Q enclosed, it's capital R, right? That's not the little r. That's the max amount of charge you can enclose. So as you get further away, it's the increase 1 over r squared dependence. You're getting E field that's weaker and weaker. So E field is 0 at the origin and also 0 at infinity. And it peaks at the surface. So that's Gauss's law. You can see the calculation is so much simpler than what we have done previously. That's the beauty and why we like to use Gauss's law when the symmetry allows. So what I mean by symmetry allows is that you have those two conditions met. 1, E is parallel to dA or perpendicular to dA on some sides. 2 is E is a constant on this Gaussian surface so that you can take it outside of the integral like we did here. Okay, so that's one of our examples. Now let's do a couple of more questions. Here's one of them. This one I will let you discuss in the breakout rooms for a couple minutes, okay? You can make sure you take a screenshot before you go. Okay, 10 more seconds for a last minute vote. Okay, I'm going to go ahead and close this and then we can take a look. Here is our results. We're kind of tied between C and D with the difference of whether 2 is 2 also works, but 1 and 3 seems to, you all think 1 and 3 works. Some of you actually, a lot of you choose 1 only. 1 only would be the answer for a certain kind of question. So let's take a look at this together. Let's take a look at our question again. What is the question? It's asking which of these surface, the flux through the surface will become something that looks like this. Okay, if we take a look at lambda L, now what's lambda L? Lambda is charge density, line charge density, L is the length. So lambda L would be the total charge, right? So it is asking the flux, which of these surface, flux through the surface is a Q enclosed over epsilon naught. So, which means the flux is what? Flux is E dot into dA. So it's asking whether this is valid for surface 1 or 2 or 3 or 4 or some of them. What do you think? Nobody choose 4. So first, can you tell me that why 4 doesn't work? What's wrong with 4?
It's not a closed surface, so all the charge isn't contained within your Gaussian surface.
Yes, very good, Jennifer. 4 is not a closed surface. And remember, we want this to be true for a closed surface. Closed. So it's not closed. So 4 is out. So the rest of them are closed, right? You agree? They're all closed. So does that mean all 3 of them works?
No. The only reason why I would be against 2 is because your dA vector, you would have some factor of pi in your flux, and there isn't.
Okay, the question is not asking whether Gauss's law is useful. It's asking, is Gauss's law valid? I would say this would be so hard to calculate. It's basically impossible. Because E everywhere here is so different. You need probably a computer to do this, numerical calculation to do this. But it's not asking what E and dA is for specific points. It's only asking when you do find the total flux, is it gonna be equal to Q enclosed over epsilon? Yes, right, yes. So Gauss's law, again, this is a question asking you if you remember that Gauss's law is always true, no matter, regardless of the surface you choose. You can choose a surface that looks like this, however you want. Gauss's law is still true. Now 1 would be correct if I'm asking which one of these can actually help you to find the E field away from the center. Then yes, remember, I'm glad you remembered the cylindrical symmetry. It's actually one of the very few symmetries we can actually solve with Gauss's law. And hopefully we'll have time to solve this problem today, line charge. So all 3 are true, but not all are useful. So now let's asking a question regarding whether something is useful or not. I realize my screen is not updating. Let me do the share again. So this is a question asking which of the surface can actually be useful to find E. Right now, your goal is to not just find the flux, but find E. Okay. Okay, I'll let you again discuss this for a minute or two, and we can vote. Now make sure you take a screenshot of the picture before you leave. Okay, 10 more seconds. Okay, I'm gonna go ahead and end the poll. Majority of the answers are for B, 1 and 2 only. And okay, very good. Let's take a look. So I realized in order to choose the shape of the surface, you must have already discussed the direction of E for a uniform surface charge density with the infinite sheet. Okay, so I want to ask you, what is the direction of E for such a charge distribution?
Straight up,
Okay, away from the sheet, right? If it's
away
not
from the
here?
sheet.
Okay, excellent. I'm glad that we remembered our stuff. Away from the sheet, over here like that. So below, then it's going to be pointing down. So if you look at the infinite sheet, I have sort of a picture here. This is how you can use sort of symmetry argument to help you understand why it should be pointing up, right? You can see that wherever you are, right, the x and y component of the E will cancel out, leaving you only directly pointing perpendicularly away from the sheet. And it's only true because you're looking at an infinite sheet. If it's a finite, that would not be true. But you know that in real life, we don't really have something infinite. Infinite is really just a model, an abstract model. So, so a lot of times you see the language of a large sheet of distribution, or that you're looking at a point that is close to the sheet, meaning that when you are really close to something, right, looking to your eye, it looks as if it's a very large sheet, right? If you go further away from your sheet, the sheet looks small and it's not an infinite sheet. So you see those languages all indicating that you can treat it using the infinite sheet model. So E is pointing away from the sheet if it's positive charge. Okay, and now going back to Gauss's law, we realize as long as our surface satisfies those two conditions, we already know our E is this way. Okay, this way and this way. So you can see that both 1 and 2 with our top surface is flat. So our dA is also pointing up. dA is pointing up, right? This one is a sort of a sideways cylinder. Your dA for a cylinder is this way, sort of pointing in all different directions depending on where you are on the barrel. So it's not always perpendicular parallel to E, so that wouldn't work. Likewise, your dA is in the r hat direction. Again, it's not parallel to E. So 3 and 4 would not be useful to find E. However, 3 and 4 still has Gauss's law true. It's just not going to be able to let you take E outside of the integration. The 1 and 2 is useful. And it is interesting, you might wonder, how come I choose a different shape and that's not going to affect my results for E? So let's actually solve this again together. You probably still remember this from a previous class, but let's just review them real quick. So here is our second example. We did the solid sphere. Now let's do an infinite sheet distribution. Sigma. And using symmetry argument that we have concluded, our E is in the, you can call it K hat direction, or Z direction. So I'm going to choose a cylinder. I can choose a cube, but I'm just going to choose a cylinder for demonstration using Gauss's law. And this is my dA on the top, dA on the bottom, and the side. Okay, so Gauss's law. Let's use Gauss's law. So realize that we have already answered the question that E is parallel to dA. The second condition, for the second condition to be met, we need E to be constant on the surface. So in this case, we realize we don't have to consider the barrel, the side, because E is, the dot product is 0 actually. We don't have to worry about that. It's really just the top and the bottom surface. So also again, can you convince yourself that E here is the same value? So this is our surface. So E here is the same value as long as you are on the surface, on the flat surface parallel to your sheet. That's our second condition. So let me ask you this in a different way, meaning that E is a constant on the surface, meaning that you can shift your point to the left or to the right, forward, backwards. It's not going to change your value. Do you think so? And yes, if yes, why? Why can we make such an argument? You can move to the left-hand side a little bit or move the right-hand side a little bit. It's not going to change your E. Why not?
Is it because your Q enclosed is the same and you're the same distance away from the sheet?
Yes, you are at the same distance away. But once you're, but here our argument, what are we caring is, once you're at the same distance away, moving left to right or backwards and forward does not affect your E. So my argument is, if we call this an X and Y sheet, right? And this is a Z. I'm saying if Z E has a dependence, it's not going to depend on X and Y for sure. So how come I can make that argument? It doesn't depend on X and Y.
I don't know, it seems a little, I guess, trivial in the sense that the E field is going to be pointing perpendicular to the surface always. I wouldn't understand a scenario where we were given an infinite sheet and it would point in infinite directions.
We're pointing in the Z direction. That is true, but I'm asking about dependence. Direction, dependence are two different things. So I'm asking, yes, you're right in the sense that they are always coupled. Once it's infinite sheet, then that means it doesn't depend on X and Y, and why not?
Is it because your charge density is constant?
That has a lot to do with this, but I can make a situation where I have, so, okay, let me word it this way. If it's a finite sheet, then that's not true anymore. If you have a finite sheet, it will depend on X and Y, but you have an infinite sheet, that does not depend on X and Y. And why that is. You may think it is trivial.
That's because at any point along the positive X, negative X, or positive Y, negative Y, X is only going to be pointing in the Z direction, right? Versus if we had a finite sheet, it would be pointing out along the edges, correct?
You're right. That's why when I'm saying that infinite sheet giving you the pure z direction and the dependence that does not depend on xy, they're coupled, come in coupled. But the way you elaborate it would be different. So in this case, I would argue because it's infinite in what way is in x and y. X is infinite, y is infinite. So it doesn't really matter you move along in x or y. You still, it doesn't make any difference. You look at the sheet looks exactly same to you. Versus if you have a finite sheet from 0 to 10 meters, whether you're at 5 meters or 6 meters is different. Right now it's infinite. So however you want to move along would not make any difference. You have, if you're looking at here, to the left-hand side, you have infinite, to your left, you have infinite, to your right, you have infinite in front of you, you have infinite behind you. So no matter which way you move, x direction or y direction, because your source is extending in the x and y direction, make your E field definitely would not depend on x and y. Again, it's a sort of an argument on, kind of like a symmetry argument that because your source is symmetric in that way, so it's not going to have those two dependence. That argument we actually use a lot later on in chapter 3 when we try to solve potentials. We use this kind of arguments. So, okay, so again, you can see, again, you are so comfortable with these, you don't even need to think about it, but that doesn't mean those steps are trivial. In fact, we made two arguments that E is parallel to dA and E is constant on the area. We did meet those two conditions. So let's finish the calculation. So this closed area has three sides, E, A top, A bottom, and E dot dA on the side. E is perpendicular, and I don't need to calculate this point. I just need EQ closed over epsilon naught. So top and bottom, you realize E and dA are always in the same direction. So dot product is positive for both of them. And top and bottom are the same area, so you get 2EA. And how much charge you're enclosing, you can realize that is this much charge. It's going to be sigma times A, right, over epsilon naught. So cancel the A. E is epsilon sigma over 2 epsilon naught. And you can see that the actual area doesn't matter. You can choose a square, you can choose a circle, the size, all of that doesn't matter. E is actually a constant above an infinite sheet. So it turned out that it doesn't depend on Z either. Because it's infinite sheet, you go a little bit further away or a little bit closer, it doesn't make a difference.
Cool. Just with infinite sheets, like for what if we had infinite rod? Would be some dependence on distance at all? Would it be the same scenario where there is on
Infinite rod, we will solve that right after this one.
Okay, sorry.
No problem. Thanks for asking that. So E will be this. And again, let's put in directions. E is sigma over 2 epsilon naught Z hat at above the sheet, but below it is actually pointing in the negative direction. So Z less than 0. So that would be your complete solution. Okay, so that's Gauss's law application for an infinite sheet. There are only a handful of symmetries that we can use solving Gauss's law. So I want to be able to summarize all of them. So, so point charge. Can we use Gauss's law for a point charge? Say yes or no.
Yes.
Absolutely. Can we use Gauss's law for a hollow sphere? Is a sigma only on the surface?
Yes.
Yeah.
Yes, absolutely. Very similar to a solid sphere with uniform charge density throughout. So this would be rho and this is sigma. So it's just the way you calculate your Q enclosed would be different. Can we use Gauss's law for a infinite line charge?
Yes.
Yes, we just did that. And in fact, we will solve one of them using sort of a cylindrical surface. Can we use Gauss's law for a, what do I call it? A hollow cylinder with charge on the surface?
Also, yes.
Yes, we can. What about a solid cylinder?
Yes.
Yes, we all can. Okay, infinite sheet. Yes. This is more like a slab. It has some kind of depth. Can we do that using Gauss's law? It's infinite in the x and y though. Does this work?
Yes.
It also works. Because I'm sorry, go ahead.
Oh, I said because it's enclosed. So yeah.
Yeah, you will have a homework on the slab thing. So you will have some practice. Let's look at, before we solve this one, I want to show you where a few other scenarios and ask your opinion. What about a line charge array? Can we solve using Gauss's law?
Yes.
And what kind of surface would that? First of all, in order for you to use Gauss's law, you should be able to find a surface that E has to be always parallel to dA on the surface, and E has always to be constant on the surface. Can we find such a surface? I'm sorry, someone said something I didn't hear.
Yeah, we were just thinking we could just make another ring on the out, yeah, enclosing the ring that we're given.
Okay, so like this?
Yeah.
No, not like.
So before we jump into finding a surface, you may want to look at the direction of E. So if you have a ring, right at the center, you would agree that E would pointing directly upward, right? Right above the center of the ring, right? But once I shift a little bit to the left or the right, do you think my E is still pointing directly upward?
No.
Yes or no? If I'm shifting a little bit to the right, you can see I have more charges on my left-hand side. These charges will give me an E field sort of kind of in this direction, pointing away. I have less charges on my right-hand side. These charges will give me E pointing sort of to this direction. They're not gonna cancel, leaving the Z direction as I was having in the center. Okay, so you can see that E will change directions if you shift. As the same likewise, you can shift a little bit to the left and your E will change directions. So, and then the way that E change directions is not like how a sphere works. It's not in a radial direction. It's not perfect radial like that. It's really hard to describe the direction of E at different locations. So how do we find a surface that works then we cannot really find a surface that works. The answer is none. Then we cannot find such a surface for those two conditions to be met. Actually, this is not solvable using Gauss's law. It could not work. You could go back and try yourself to think about this if you want a ring-shaped, a torus-shaped surface or spherical, you realize it would not work. Likewise, if you have a donut with charge here, does not work. This is a disk with a charge distribution sigma. Can this be solved using Gauss's law? Disk, you can think of disk as a superposition of many rings. So a ring doesn't work. Can a disk work? You can use the same argument as if you're
No.
directly above it is like E. But if you shift a little bit, E will shift. Flat, yes, it's a flat surface. It cannot use Gauss's law. No matter if you choose a cylinder or sphere, it would not work. A cube actually is a no. Even though the charge itself looks symmetric, doesn't mean you can use Gauss's law. The only problem that can be used using Gauss's law are already listed here. These situations, I may have forgotten something here, but that's all I can think of. These situations are tempting, but you cannot use Gauss's. Okay. All right, so now let's actually solve the line charge distribution. You can have a line lambda infinite long, or you can have a coated rod or a hollow rod, or you have a solid rod. Sometimes they use a language of infinite, or they will say it's a thin rod. Okay. Those are indicating you can treat it as infinite long. Thin means that the radius A is so small compared with how long it is. That's why it's thin, and they can treat it as infinite long. Okay, so all of these situations, first of all, let's find the direction of E. I'm gonna use lambda, this as an example. I have some charge distributed on this line. So what is the direction of my E?
The Z direction?
Upward, yes, pointing away from your rod. Very good. Now you could do this exercise by evaluating a little chunk here, right? So give you a DE this way, and you can always find a symmetric point that give you a DE that way, giving your overall E this way, right? Because it is infinite long, you can always, whichever you find here, you can always find a symmetrical point on the other hand. It's infinite long, right? So this kind of addition always works. So that's your E. Okay, so now that means my Gaussian surface, I will choose a cylinder, which is at a distance R away from the rod. Okay, so let's do this together. E for the outside. Okay, E, I only need to calculate E on the side. Top and bottom sides, I don't need to calculate because my dA is perpendicular to DE, right? So because E dot into dA top is 0, E dot into dA bottom is 0. So I only need the side. Okay, so the E, the area of the barrel, area of the side. So what is the area of the barrel? Anybody?
Pi r squared.
That would be the area for this. Two pi RL. Okay, thank you for the answer. 2 pi RL. Okay, so if we forget, there's a way that I can maybe help for you to remember the side of the barrel. Okay, think about a cylinder. If you unroll it, sort of cut it open, it kind of becomes a rectangle, right? So one side of it is L. This is L. This is the one you wrap around. So this is the circumference of this other side with a radius r. So it's going to be 2 pi r circumference. So that's why the area of this barrel is the area of the rectangle, 2 pi RL. Okay, and Q enclosed is a line charge. It's going to be lambda times L over epsilon naught. We cancel my L. I get my E is lambda L. I'm sorry. Lambda 2 pi epsilon naught R. Okay, so it's pointing directly away from the rod. So this is for rod. For this and this, they're very similar. Well, just to give you the Q enclosed for those two situations. This one will actually have Q enclosed as in sigma times, again, you're enclosing these charges. The charge lives on the barrel. So it's the surface of the barrel is 2 pi AL over epsilon naught. That's your right-hand side Gauss's law. Here is rho times, it's the volume of the barrel is pi A squared times L over epsilon naught. So you can calculate your E field for all three of these situations. And that's, they're very similar. Okay. So we have 5 minutes left. I'm just gonna touch briefly upon electric potential, okay? So I wanna ask you, let's just simply do a brainstorm, just recall all the stuff we remember. From your intro physics course, or whatever course that you had before, what do we know about electric potential? Anything you can think of, I'm gonna write it down. What do we know about electric potential? I'm sorry, go ahead.
I remember it as voltage.
Okay, very good.
It's a scalar.
Scalar, excellent.
They're created from electric fields.
Oh, it's created when there is an electric field exists. Okay, anything else?
It stores energy.
Yes, it is related to electric potential energy. I agreed. That's U. Anything else we remember? What is how about the definition of electric potential? How is it defined?
The flowing of the flowing of, is it electron?
Is it the integral of E dot dl?
Ah, okay, so V is defined as integral E dot into dl. Very good. I also see someone said dV is E dx, so it has to do with the differential format, yes. So in fact, yes, V is defined to be negative E dot into dl. and we define it, we need a reference point because this is integration. You need the limits, right? The limits is from a reference point. We use like a curly rule O to represent a reference point to a random point R in space, and that gives you V of this point in space. V at R is equal to negative in reference to R E dot into DL. So you might notice another way of writing this is E as a vector is a gradient of V. V is a scalar. This is gradient of the scalar. The negative of that is give you the electric field. Okay, all very good, excellent. That's all we remember from the electric potential. Okay. So I'm gonna give you a few quick notes from our, what did we do? From our 133, 1520, you may have noticed that V is KQ over R for a point charge, right? Now voltage is related to electric potential energy, as you said. Energy over charge, giving me potential, giving me the voltage. Now delta V, sometimes we're talking about a potential difference. The difference between the potential at two different points. This is path independent. Only depend on which 2 points are. It doesn't depend on what path you take to do the integration, as in E dot into DL. So another way to write this is using the derivative. If you take the derivative of V with respect to R, you get E. So sort of if you treat V as in feature in space, they all have different V, right? And sort of you're taking the gradient, the one that is have the greatest fall of the potential gives you the direction of E. Okay, so that is all the stuff we remember from intro physics. Okay, the reference point though, as most of the time we define infinity to be our reference point, because this is really a delta V. Right, delta V is potential between two different points. Let's say point A, point B minus point A. Okay. Delta V difference between A and B is negative from A to B E dl. Okay, now this becomes V B minus VA is negative A to B E dl. So if I want a V at any random location R, I'm going to say, let's choose A to be our reference where potential is 0. So it's becoming from reference to R E dl. Okay, so most of the time we choose V infinity to be 0. So that's our reference. So our integration most of the time comes from infinity to R E dl. So we will continue with that discussion next time. And then we will try to solve some problems for involving electric potential. Okay, so that's all for today. I will see you guys next week on recitation, actually, on Friday.
Got it. Thanks so much, Dr. Ryan.
Bye. Thank you, everybody.